Thank you, Jesse. That was scary. But now it's time for the lightning talks. And first up here is Tony, who's going to talk about the DNS changer. And yes, I'll just leave him. Thank you.
All right. So as you can see, for those of you who know Marike, I'm not her, and she was unable to attend to the last minute because she hurt her back and can't drive the distance it takes to get here. So I offered to present the slides on her behalf because I have some familiarity with the subject matter too. Could you reset the clock, Greg? All right. And it's also a timely topic that's important, so I didn't want it to get missed this time. So we'll just talk briefly about what's DNS changer, what the takedown, what happened during the takedown and replacement of the seized servers, customer infection, remediation, statistics, efforts, and what happens on July 9th, which is only a little more than a month away. So for those who don't know, DNS changer is a malware that changes the DNS settings on victimized machines and also tries to reconfigure the home gateway to point at DNS servers that were operated by a criminal enterprise of folks that were mostly located over in Europe, and there was a coordinated law enforcement effort to take down these, to arrest these individuals, take their assets, and prosecute them. And basically what it was to make money off of illegitimate ad insertion traffic. Here's the net blocks involved. What happened during the takedown was that the seized servers, which were actually physically located in the U.S., were replaced by ones that operated normally and generally gave correct answers. And so they were put in the place of the existing servers on the same existing address space, and the same ISPs were continued to advertise that address space, so that there wasn't an interruption of service, a blackout for all the people using the bad DNS servers, for them just because of them just going away. That was back in November, and this is kind of just a quick cartoon about how it happened. They took the servers on the left away and inserted the ones on the right to pick up the traffic. So what happened after that is also they took the information from the logs of the servers about who's hitting them to give a sense of the affected machines, so that then the people who own those machines or the people who were upstream of them could notify the users that their stuff was broken, that they could get well. And this ad hoc DCWG, which is DNS Changer Working Group, was formed to do this work and generally promote the remediation of the infection. Under an existing thing that ISC does called the Security Information Exchange, SIE, the information is published if you're interested to receive the detailed information about who's hitting the servers and who among your user base might be infected. You can do that. There's information on the dcwg.org website. There's also information there about how to detect whether you're infected in local languages. There are websites you can hit that give different visual responses based on whether or not you're hitting the replacement servers for DNS resolution or not. And there are some cases where it'll return a false negative because there are some ISPs that have chosen to redirect to basically carry internal routes for that address space and point it at their own internal DNS servers. That's all done with a positive outcome in mind, which is to keep their users running and also to be able to internally detect whether which of their users are affected so that they can notify them and help them remediate. There are tools that have been worked to try and help clean it up. Unfortunately, this malware is really nasty. It affects the master boot record and often actual reformatting the disk is the only thing that'll really fix it. But there's also cases where it's updating the home router. Let's see, I think that's in the next slide. There's a number of ones that, since obviously probably everyone here knows that the many home routers ship with the default config and user login credentials, it'll try and exploit those to reset the config of the router, not actually install malware on the router, but that's one nasty aspect of it. So this is a little cartoon that was supposed to show essentially what happens, how an affected home router can make it appear that devices behind it that are not even affected with malware, like a smartphone or a printer or what have you, will also may show up. So if you try and get to the website that shows the different green or red based on your infection, you may see it on a device that's not infected but affected because it's downstream of a device that's using a compromised DNS configuration. Here's some statistics about the overall trend of the remediation of the detected affected machines over time, and there were some spurious spikes in the beginning, but it all started on November 8th when the replacement servers were put in, and it's been trending generally downward, but it's been about 40% remediated by this metric, and there's still well over 300,000 apparently affected people, although that may be something where there's a number of devices behind a NAT, even an enterprise firewall that's masking some larger number of infections. But this is the coarse-grained view. Here's a little bit more detail that was provided by some folks in Germany about different events in the remediation effort, including publicity campaigns and rollout of their specific native language detection site to show that, how this helped, but still obviously lots of infections. So part of this is all thinking back to Jesse's talk, it's a bottom-up community organization involvement, and trying to figure out, what went well and what didn't is a little bit of the exercise. People have probably seen discussion on the NANOG list about, well, I've got this notice from the FBI or my ISP, and it didn't make sense, or I didn't care, or what have you. So that's all part of the learning experience, and more feedback is appreciated, constructive feedback. So what's going to happen is in less than a month's time, slightly more than a month's time, the court order will expire that provides these replacement servers. So people who are still pointing at them will, we believe, go offline because they won't be able to resolve DNS. It's possible that some operating systems will fall back to dynamically learned DNS servers. So it's not completely known what will happen with all of them, but there may be a wave of extra support calls. If you have relatives who you'd like to check out their configs, that would be helpful, because better that you do it proactively while they're still online before they just call you and say, what happened to the internet? This is a cat picture that Marike put in. Okay. So any questions? I do have some familiarity with the topic, but I can't necessarily answer everything that she may have put in here. Questions, comments? All right.
All right, thank you. Can you hear me here? No? Oh, there we go. Sorry. Next up is, sorry. Gosh. Yep, well done. That's Shane Amante from Level 3. There you are, thank you. And Shane is going to talk about resource certification using DNS and IRRs. Thank you, Shane.
Is this to forwards? Yeah. Okay.
Yes.
Cool. Hello, everyone. I'm Shane Amante from Level 3. I'm here to talk about resource certification using DNS and IRRs. Some things that I've been working on with some collaborators, my colleagues at Level 3, and also Eric Osterweil from VeriSign. So, broadly, I think there's probably agreement that the three horsemen of the internet is three things: the IRRs, the Internet Routing Registry specifically, is what is encoding routing policy information, what is the intent of what is an AS wants to originate or effectuate from a routing perspective. You have the output or the results of the policy information carried inside BGP, that's routing, that's reachability information. And then last but not least, you have DNS, which is naming, right? Naming is obviously very important because that's what gets everyone to their the destinations without having to memorize IP addresses. So these are three very critical systems that are already deployed, scaled, being used, and they have been for well over a decade, if not longer. So the question came up as to why not just use the IRRs for resource certification? And usually the first answer you get back is the IRR sucks, period. And then you ask, okay, well, why, what does that really mean? Because there's aspects to the IRRs. There's the data portion of the IRRs, and then there's the routing policy specification language, or RPSL, the latter of which is a very rich syntax which is very expressive and allows one to express many things from a routing policy perspective. And usually the concerns are not around the RPSL, but around the data or the quality of the data. And that's really what the fundamental issue is I don't really know what data within the IRRs to trust. So the question I ask back is, can we actually improve IRR data quality? And I believe the answer is yes, with a light assist from DNS. So the question is, well, why DNS? Well, why not? Obviously, I'm not sure how many folks are aware, but DNSSEC is deployed for reverse DNS. We've, in fact, signed several /16s through Aaron already. It's a very quick, painless process to actually set up and works just fine. I'll talk about that in a couple of slides. The other important points worth mentioning is that in DNS in particular, there's a single root, obviously, and there's a single trust anchor that is deployed for DNSSEC that's operational today, which is all good. Obviously, given the operational experience we have in deploying DNS for the last couple of decades, there's obviously substantial resiliency and scalability to DNS. And by that, you can easily think of a couple different scenarios. One is Anycast DNS is a mechanism that's widely deployed on the internet for high availability reasons, as well as the capability to deploy multiple name servers. And obviously you should deploy multiple name servers across multiple networks, of course, for maximum resiliency. If you don't know how to do these things, then perhaps you should be looking at a provider that does do these types of things and then trust them with your DNS. And then last but not least, of course, there's obviously a massive amount of monitoring, documentation, training, tools, et cetera, that have been built around DNS for the last several decades as well. So it'd be very nice to leverage that same already deployed infrastructure, if possible, to provide resource certification for internet numbers. So how could such a system work? What we would propose is that one takes and builds, first and foremost, you actually go and build in your reverse DNS using the nomenclature provided in that draft Gersh DNSOP reverse DNS CIDR. The IP prefixes and origin ASs in what are called secure route origin resource records inside DNS. I'll show you a little example of that, and in fact there's a talk that's on Tuesday that's also showing some examples of that, but I encourage you to go read the draft and you can see more details about it. Obviously, once you've encoded that information inside DNS, you've signed the zone with DNSSEC, obviously, to ensure that it's secure. The next step would be, how do you validate against that? Step two would be actually using the existing mechanisms that we already have today. You actually build a candidate IRR origin list using your favorite IRR toolset flavor, whether it's homegrown or one that is open source. And you effectively are coming up with a set of IP prefix origin AS pairs. Next step would be, after that, you actually go through and you verify each one of those IP prefix origin AS pairs that you pulled out of the IRR against DNSSEC. So you're looking up an IP prefix and you're looking to find and make sure that the AS or origin AS actually matches in the DNS reply that it is what you pulled out from the IRR. And then last but not least, obviously, if it matches, then you have effectively a secure route origin. If it doesn't, well, obviously something's broken. So here's a little bit more details of what the DNS lookup process would actually be. Obviously, you know, there's only 3 steps here. It's hopefully pretty simple. Obviously, if the DNSSEC SRO resource records set matches what you pulled out of the IRR for an IP prefix and origin AS, it's valid. You have a signed authenticated response following the DNS hierarchy, that's a valid origin. Obviously, if that's the case, you can include it in either IP prefix lists with origin AS matches inside routing filters that you're going to apply to routers inside your network, or you could just use it for offline manual verification if you wanted to do that, and use that information as you want to. We already talked a little bit about the second step was if it's invalid, if the DNS SRO resource record set does not match what you pulled out of the IRR, then it's considered invalid. You should not include that in your IP prefix list. Step 3, obviously a little bit more tricky. What if you get a not found coming back from DNS? What if you don't know what to do with it? Well, if it's a more specific that you have already validated a covering aggregate because you've basically pulled a less specific covering aggregate out of the IRRs and you validated that against DNS, and this is most likely a misconfiguration case where someone forgot to go encode the more specific inside of DNS. So I say go ahead and trust it because you have a covering aggregate with the same origin AS for it. On the other hand, if you consider that the prefix and origin AS does not match a valid aggregate, then it's invalid and you drop it. To give you a couple of examples of the encoding inside of DNSSEC, this is an example of a couple of prefixes that we've encoded of various prefix lengths. You can see there a /20, a /22, a /24. In fact, you can go and run these same dig queries yourself at your leisure and verify that they actually do match. And then last but not least, as far as conclusions go, hopefully everyone agrees that using DNSSEC for resource certification is actually a pretty straightforward process. Actually using DNSSEC and IRRs is also a very good thing because it's leveraging deployed systems that we have decades of operational experience and tool chains and training already built and available. So with that, there's about a minute for questions.
Hi, Doug Montgomery Ness. Why would you bother putting prefix origin information in the DNS to validate prefix origin information in the IIR? Why not just take something else in the DNS, if you like its trust hierarchy, and digitally sign the route objects in the IIR?
I'm not really sure what you're alluding to, but this is a very lightweight encoding scheme that's using the existing in-adder address.arpa tree that is signed. This is just a naming convention of what you use inside of DNS. So it's already there and it's
duplicating
usable.
prefix origin information in the DNS to validate prefix origin information in the IRR.
Correct, because there is no deployed security authentication mechanism in the IRR itself. Unfortunately, it's not widely available. So what can I actually use? And DNSSEC is basically an answer that has a single signed root that allows me to do that.
But it only validates one piece of the route object. If I was going down that path, I would just digitally sign the route object.
So maybe the piece that you're not understanding is that when I build prefix lists and origin AS filters that I apply towards my customers, I already have a tool chain that's built around pulling information from the IRRs, which gives me a fully enumerated list of IP prefixes and origin ASs, which then I can very simply walk through one at a time and validate, and if I get an authentic signature back, I can then say with assurance that that is a valid origin AS tied with that particular IP prefix. So it gives me an enumeration capability is perhaps the key thing that is what I'm trying to say here.
Okay. Guys, please remember one question per person, and we need to wrap this up rather quickly. Thanks. Rudiger, you're first. Rudiger.
Sandy.
Okay.
Okay. Sandy Murphy, Sparta. There's been suggestions, Rudiger was one of the ones who first put it forth, to do something to use the ROAs in the RPKI system to produce something like route objects that can be used with the existing tools to build filter lists. There's also a draft before the CIDR working group in the IETF right now to use RPKI certificates to do authentication of information that's in the RPSL. It's the RPSL SIG stuff. Where was I going to go? There's a subtle difference in the semantics of the SRO and the ROA object in the RPKI and the route object. Have you looked at the way the RPSS, the defined security system for IRRs, defines the authority for route objects?
So again, I'm not here to talk about the RPKI. I'm here to talk about existing tool sets that are already in use in the internet.
I'm talking about the things like the IRR power tool set, like the PE eval and all those sorts of things. You can use you've discussed.
I'm not using the RPKI currently.
I know you aren't.
And so I don't have any ability to extract
use it.
information from the RPKI and stick it into, and quite frankly, I want to stick with the existing systems that I've already got deployed and leverage those as my path going forward.
Okay. Is there, you're talking about ways to improve the route object data that's in the IRR with the data that you're doing in DNSSEC.
Correct.
Do you think you will take a look at what is being proposed to use RPKI data to provide authentication for IRR data?
So I'm familiar with that work, but I'm not here to comment on it.
I'm asking you whether you would.
No.
Thank you for your refusal.
Sam Weiler, Sparta. So you're talking about how the reverse tree is very well signed. Catch is the reverse tree doesn't currently have a naming convention for net blocks, or in this new one that Gersh and others are proposing. And when I've looked at that naming scheme, what it looks like is not quite a parallel tree, but sort of an overlaid tree, where it's actually not fully deployed. And so you talked about using this in some /16s, which I can believe. But I think that using it in a /15 would actually be very challenging right now. Is that accurate?
So that's accurate in so much as you need to, we would need to get cooperation from the RARs that would hold that reverse tree to do this naming scheme. I'm not necessarily a DNS expert here, so I would actually defer you to Eric, who's actually at the mic, that can probably give you a better answer.
I have to cut you out. I'm sorry, Eric. But I have to make a commercial for the DNS track in the afternoon, and I think that would be a great place to continue this discussion.
Can I just say one thing, like meta comment, really
Like
quick?
20 seconds.
20, I'll do it 15. I think on Shane's second or third slide, he pointed out that the IRRs are giving him policy semantics that don't exist in a lot of the other systems you guys are talking about, and I think that's why he threw those in there.
Yeah, no, Rudiger, no.
What policy definitions has Shane
No.
actually
We're going to have a discussion about tomorrow as well, because we have more presentations in this subject. You will get more. And welcome to Edward from Google.
Hey everybody, I think at this point I have like -5 minutes, so I'll try to keep it brief and get you out of here so you can get to whatever you're doing. You know, Google likes to talk about OpenFlow a lot. OpenFlow in general has the hype machine running on it pretty hard right now. There haven't been a lot of real deployments. As far as I know, we have the world's largest OpenFlow deployment currently in terms of total state managed, total number of nodes deployed, total POPs, pretty much you name it. So I'm going to talk a little bit about that, and I'm also going to talk about how we did it, if there's time. So Google has a big network. You probably knew this already. If you believe Craig Labovitz, which I do sometimes, in 2010, we were the world's second largest network. This is before the agglomeration of Global Crossing and Level 3. Thank you, Shane. This was only our front-end network, though. Our back-end network is actually much larger than our front-end network. And, you know, this is the standard boilerplate for Y. I think some of these numbers are inaccurate at this point. I think we have 72 hours of video every minute, which is like 1.2 hours per second. So anyway, yeah, it's big, and we push a lot of content over it. We actually have two different backbones. We have internet scale backbone, which is what the Atlas metrics were on. And we have a Google scale backbone that, or G scale, which runs between the data centers. And this only runs between the data centers, and it only carries kind of bulk data traffic for us, index pushes, et cetera, et cetera. As a result of this, we have pretty widely varying constraints with regard to the loss sensitivity of the traffic classes that we're talking about, and with regard to how the topology is deployed, the overall availability of the network, et cetera, et cetera. In other words, we get to be a little bit more experimental with the back-end network, and we get to do some exciting stuff. And that is the OpenFlow network for Google. In addition to widely varying traffic characteristics between the networks, lends itself pretty well to a lot of operations researchy type techniques for doing optimization of traffic engineering. On the front end in general, you can do pretty standard traffic engineering because we have a fairly smooth diurnal cycle. There's a few exceptions to that, obviously. On the back end, though, we have extremely bursty traffic. When an index push starts, it's basically a square wave. And since we have some idea about what the schedules for these things are, we can take advantage of this in traffic engineering. So why do a software-defined WAN in the first place? What's not sufficient about existing protocols? Well, a lot of it has to do with the hardware, honestly. In doing this, we get to separate the hardware from the control plane software, and that means we get to take advantage of very cheap, fairly high-powered commodity compute. And that is a good thing. As I'm sure you all know, the controllers that you're putting in your routers are, 4 or 5 years out of date, and you're paying a great deal for them. So it's very nice that we get to make use of our bulk compute infrastructure for doing a lot of the stuff that we want to do with regard to optimization. In addition, the fact that it's logically centralized gives us a more complete view of total network state, which makes for a lot of pretty interesting opportunities in optimization, and I'm going to talk about that a little bit later. It also gives us the ability to automate fairly simply. Part of the problem with running a very large heterogeneous environment, obviously, is that you have a lot of northbound APIs in the form of different config systems or XML or et cetera, et cetera. And so having to deal with this stuff in a non-uniform way is kind of a pain, as we all know. And I think Vijay is going to talk about some of that in the not too distant future. We also get to control both the horizontal and the vertical on this network. So having fine-grained control of state like this lets us do some pretty interesting things. And as I said, I'm going to talk a little bit about that. So in general, the theory is that this results in a higher performance WAN that's more efficient, more fault-tolerant, and cheaper. Basically, we get better ROI. So where is this deployed? Pretty much everywhere. This is public information. Greenpeace actually did a really great article on data center locations recently, and modulo, the wattage. They got a lot of stuff right. So you just never underestimate the power of two hippies in Paisley with a pair of binoculars. Yeah, it's deployed globally at this point, and you can see, it's very difficult to see for me at least, I'm sorry, but you can see that we've been working on it for about the last 2 years. And that we're starting to taper off as the complete set of back-end traffic has been migrated onto the OpenFlow network. So this is sample utilization across the set of links in the network. Yeah. So we run stuff pretty hot. In general, this would obviously be problematic if we were worried about, if we were doing like standard MM1 modeling for queuing delay or any of this stuff, and we're actually concerned about that, this would not really be all that tenable. Moreover, if we were worried about standard kind of TCP transport protocol semantics with regard to having some sort of sawtooth going on, that would be a problem. Fortunately, because of the fact that we run this network and we run all of the systems that are on it, we get to use non-standard transport protocols. We also get to do a lot of fairly interesting stuff with regard to scheduling. So what are the implications for network operators? Well, the pros are that we've seen it reduce the cost of the total WAN deployment in terms of dollars per bit per second in CapEx. It's less true for OpEx currently, actually. I think that we're going through some growing pains, but there's a lot of potential here in terms of automation that would be difficult to get in other areas. We get to do less over-provisioning for SLAs. This is because the protocols that we run are entirely deterministic, modulo the demand being non-deterministic. Now, because of the fact that we actually have some idea of what we're transferring between systems, and we can schedule these things, they're a little bit less non-deterministic than you might think, but there is a certain amount of uncertainty there. However, given a demand profile, we can tell exactly what the network is going to do. So we've managed to deploy it incrementally, and we've leveraged known techniques for delivering this functionality. The cons are that, with regard to OpenFlow, there's not really any good package solutions currently for on the WAN side at least. The protocols are in their infancy. Anyone who looks at the OpenFlow spec currently and who's done protocol design before is going to be pretty disgusted, and rightfully so. The software, in order to do the sort of stuff that we're talking about here, obviously a lot of software engineers spend a lot of time on this. We did a lot of protocol design work, we did a lot of algorithm design work, and we're fortunate enough to have a really great operations research team doing optimization on this stuff. And so if you don't have those things, your mileage may vary. As I said, there aren't really any good package solutions right now, but hopefully someone will fix that. It'll also vary based on your demand characteristics. As I said, the more square wave your demand is and the better you know the schedules, the more you're going to get out of this. So, what does Google software-defined WAN actually look like? Well, this is built from our own hardware that we've been working on for a little while. In general, it's entirely built out of merchant silicon. It features OpenFlow support, which was something that we weren't able to get from any of the vendors at the time. In general, we would have liked to have purchased this stuff because developing your own hardware is a pain in the ass. Pardon my French. But we couldn't at the time. So we also used open source routing stacks, in particular Quagga, to do BGP and ISIS for the sake of the initial integration. And it's likely the BGP portion will obviously stay around for a while because we're going to have to interface with a lot of other networks. It doesn't have the complete feature set. It doesn't have your AppleTalk I don't care. Sorry. It's very cut down, and so the sort of embedded software that we write is extremely minimal. And it can be considered a little bit user-unfriendly at times, but it's also cheap and functional. So, obviously, you deploy multiple chassis per site, blah, blah, blah. So, what does it actually look like? Well, we have what is effectively an out-of-band controller array. These are a bunch of machines that are just pushing flow mods down to individual devices, and these are deployed on a per data center basis. In addition, there are Quagga machines that are associated with the controller arrays that run through what's effectively a large RIB manager, which does translation from routes to flow mods. There's also a traffic engineering server, and these two things run in parallel. And basically, basically, the traffic engineering server just pushes out stuff that represents the overlay topology on the existing ISIS topology. So in order to do this, we have a global broker, which is effectively a global scheduler. I'm not really going to talk about that all that much. We also have a path allocation algorithm, which is, you can see some of this work in the more recent Infocoms. We've been publishing some good research on upward max min fare, throughput optimization, and some other things that we've been looking at. Most of you probably don't care about max min fare, but when you're trying to schedule really big data center pushes, it can be important. So, and of course, a topology manager that has to collect state. Now, this is something of a point of contention when people talk about centralization, or even a modicum of centralization, because of the fact that people think that the control loop is going to be pretty flabby, because it takes a while to gather the state from the network and have any sort of accurate representation where you're unable to checkpoint it. You may end up either out of sync, or you're going to end up with an extremely loose and flabby control loop. I guess my answer to that would be, obviously, these are all concerns, and these are things that we have to look at. But if you look at how fast the TE control loop is right now, it's actually pretty easy to get better than it. We also have a controller, obviously. The controller basically just, as I was saying, has a Quagga associated with it and a tunneling app running off to the side. They inject mods separately. One with the encapsulation that we use for the tunnels to just direct hop-by-hop flow state, and then the other being, complete ISIS and BGP. These push things down to agents that are on the switches, which then interface with a bunch of hardware tables, and obviously there's a whole bunch of work if you're going to write your own user agent for how you're actually going to interface with whatever hardware you have. There's an additional layer of hierarchy on top of this, because obviously if you have TE, then you have some coordinated mechanism. This is actually kind of a sticking point with a lot of these architectures right now, in that how are you going to distribute state between decentralized TE servers if you're not making a complete decision on a single server? I will say it's quite difficult, and if you'd like to talk about it later, then we should. Right? Yeah, because I think that I'm out of time. If you have any questions, please step up to the mic.
Hi, Jake here, IP Infusion. Do you share any state between the I-scale control plane and the G-scale control plane at all, or is it just done through standard?
It's just
protocols?
It's just edge state, so standard protocols.
Great. Thank you, Edward. And now it's time for coffee. After the coffee break, we have the DNS track. Here, in this room. Peering. Oh my God, sorry. The peering track, not in this room, somewhere else.